So today we're gonna be going over 2021 AIME1. Start with problem 1. Z and C are practicing their 100-meter sprints by running 6 races against each other. Z wins the first race, and after that, the probability that one of them wins a race is 2 over 3 if they won the previous race, but only 1 over 3 if they lost the previous race. The probability that Z will win exact 5 out of 6 races at that moment. So we know that Z won the first race, and then we will analyze the entire thing for Z, because the question wants the probability that Z will win. So we will analyze this question on the perspective of Z. When does W, L is lost. So for the 6 races, right, he has to win 5 and then lost 1. Now, if the L is not at the end, it doesn't matter, right? For everything else, there's always at least one of the races that Z will win after he lost. So all of the cases where the Z losing on the second race, third, fourth, fifth, and sixth, they're all the same. No, on the fifths, not on the sixth. These 4 cases, these are all the same, and then the final case is another case. So these 4 are all gonna be 1 over 3 to the power of 2 times 2 to the 3 to the power of 2. Now, for this final one, he's gonna only lose 1, so it's actually only 1 over 3. And then it's 2 over 3 to the power of 4. Oh, this part's 3. This part's 3. He won 3. So now, let's combine them together. You get the answer 16 over 81, which we add them together gets you 97. Now for this question, we have a rectangle and another rectangle, and then it's asking our shaded area, which is the intersection of the 2 rectangles. Now, one thing that came to mind very clearly is that these two triangles, they're similar. It's very easy to prove. The AFCE and ABCD, they are all rectangles, which means these two are 90 degrees, and then these two are the same, so they are similar. Now, let's assume this point is G, and then assume this is X. So now, GD will be 11 minus X. CD is still 3. Do we know the similarity ratio? Yes, we do, because we know AF. AF is 7. CD over AF, which is the similarity ratio between the 2 triangles as they are corresponding lines. So they are 3 over 7, which is the similarity ratio. Now, we know the similarity ratio, so we can sum numbers in. Do we know what CG is? We know what AG is. So then AG is X. So CG is going to be 3 over 7X. Now, what is FG? Do we know what DG is? DG is 11 minus X. So what is FG? FG using, again, the similarity ratio. Okay, FG is this. And then FG plus CG is going to be FC, which is 9. And then we just solve the function. Solving for x, we get x equals to 35 divided by 4. Now what is the shaded region? We know that for a parallelogram, the area is just space time height. So it's basically 3x, which we get is 105 over 4. Adding them, we get the number 109. Now here, we want to find any positive integers less than 1000 that can be expressed as the difference of two integral powers of 2, which is 2a minus 2b. Now, first of all, we have to find a range for a and b. At the very start, we notice that if a equals to b, then this is gonna give us 0, which is not a positive integer, so that doesn't count. So, a is gonna be bigger than b. Now, what is a? When is the maximum of a? We know that 2 to the power of 10 equals to 1024, which is totally okay. The 2 to the 11th is gonna be 2048. If that is used to minus 2 to the power of 10, which is the smallest number, which is the biggest number smaller than 11, we still get 1024, which is more than 1000. Note, if this 10 goes down, this is only going to get bigger, and that's not going to help. So we get that a's max has to be less than 10. Less than or equal to 10. Now, after this, you can just bash it all out, which is not that hard. We're going to approach this a more easier way. We note that for every single pair of a and b, all of them are possible except for these 5. This is also relatively easy to prove because for all the 9s, 2 to the 9s is equals to 512. No way 512 minus positive integer is gonna be more than 1000. And if it's 2 to the 10 minus 1000, we get 24. Which the max we get is 2 to the power of 4 is 16. Now we're just gonna prove that each one of them are different. How do we prove that? It's easy. What do you think of when you have two integral powers of 2? You think of binary. For example, like 2 to the 10 minus 2 to the 5. That's gonna be 1 0 0 0 0 0 0 0 0 0. It's one more 0. 2 minus 1 0 0 0 0 0 2. Now let's see. If we assume we prove this by contradiction. If these two are equal, rearrange them a bit. And then the minus became plus. Because they are all different, they are all integral powers of 2, it's gonna be some kind of 1 0 0 0 0. And it's not gonna have any like induce or plus 1 or something. It's not gonna go up to 2. Just gonna be 1 some zeros and then 1 some zeros. Something like that. Now, because it's like base 10, there is never gonna be two numbers that have the same value but pronounced at the written out in a different way. Like 25, there's no way equals to 31. Just like how in binary, 100110 is never gonna equals to 11000. It's the same. So that basically completes the proof. that there's no difference. There's all of these are different. So any of the two numbers that are less than 10 won't work. So you choose 2 from 11, which is 0 to 10. And then you minus the 5 we listed out earlier here, which will result in a number more than 1000. We should get the answer 50. Now, we want to find a way 66 identical coins could be separated into 3 non-empty piles so that the fewer coins in the first pile than in the second pile and fewer coins in the second pile than the third pile. Okay, what we do here is we can try a smaller number and then we try to find a pattern, whatever, and work our way to 66. So let's try 6 coins. For now, we're just gonna try to list it out and list all of them out because there's not enough. Then try to find the pattern. I guess it's too small. We need a bigger one. Let's say 10. We still couldn't see quite much. Let's try 15. Okay, you can see here now we have 5 here, 4 here, 2 here, and 1 here. What would be the pattern here? If you look closer, you can see that this separates by 2, this separates by 1, this separates by 2, this separates by 1. Now after this hint, you can clearly see that it's going to be 3 in the middle. 1, 2, 4, 5, probably 6 in the middle, 7, 8, and then goes on. Yes, and that's the pattern. We have no 6, no 3s, no 9s. So, how about 66? What is the number here? It's easy. You can just write all the things that start with 1. And it's not hard to write all of them because you can skip them because you can know that the two sums it gives you 65. And then you just 32 minus 1, you get 31. And then you skip 30, 29, 28, 27, 26, 25, 2, 1. And then you find a sum. 31 plus all the way to 1. You minus out the ones that can divisible by 3. And then this part is just 31 times 32 divided by 2. Take this 3 out. 10 times 11 divided by 2. And which you get the answer, 371. We have a arithmetic sequence here. And then the three terms, sum of the square of 3 terms equals to the product of the middle term and the square of the common difference. What we can immediately think about is to assume them, right? That kind of helps the problem, give us a bit of idea of what's going on. Now, let's write the equation out. Sum of squares. The product of the middle term and the square of the common difference. The reason why I assumed it like this instead of a plus b, a plus 2b, is because you can actually cancel the 2ab term here, which makes things a lot easier. I mean, it's not impossible to set it like this, but what makes it harder, right? Now, we only get equation with these things. Rearranging, isolating b squared, we get this. And then we keep simplifying further, we get this. Now, b squared, a and b are both integers. So 12 divided by a minus 2 has to be integers. Now, so a minus 2 has to equal positive negative 1, positive negative 2, positive negative 3, positive negative 4, positive negative 6, and positive negative 12. Now, we test all of them one by one. And then you find only when a is 5 or 12 it works. Oh, or 14, not 12. Which give us b equals 5 and 7. And then we get the answer 31. We have a cube here, and then AG is a diagonal through the center of Q. Then we have a point P, connect a few points, and then we know these results. Now we need to find AP. Well, one thing at first is like, these numbers, they're a little bit too big. We just scale it down by 12 for simplicity purposes. So now BP is like 5 root 10, CP is 5 root 5, DP is 10 root 2, and GP is 3 root 7. Now this problem looks like it's a geometry problem, but it's not quite a geometry problem. It's more of an algebra problem than a geometry problem, because there's not a lot of geometry theorems that you need to know to solve this problem. So we just simply assume P is x, y, z. Now, it's very easy to write 3 equations. Just bash BP, CP, and DP out. That's exactly what we want to do. Now, the silence of the cube, we assume it's going to be S. So now, BP is going to be S minus x squared plus y squared plus z squared equals to 5 root 10 squared. Now, note that if it's like this, right? This is like the height, and then these two are the bases. This, connect this, and this. They are still perpendicular to each other. These are perpendicular, and these are also perpendicular. So if this is A, this is B, this is C, then the length of D is still going to be A squared plus B squared plus C squared, due to Pythagorean theorem. Now, after we know this, we can write all of these out, right? Then dp okay, now what is GP? GP is a bit important. Here, at these three, we just switched one element out. But at G, you gotta switch all 3 elements out, right? And then this is just basically 250, 125, 263. Yeah. After this, what do we want to find? We want to find AP. What is AP? AP just x squared plus y squared plus z squared. Alright, let's see. How could we get x squared plus y squared plus z squared? Now, what you want to do, usually when you see these questions, is you want to find out what kind of symmetry is in here. If you add on these 3, if you consider these 3, they don't work when they go along. They only work when you add them together. Why? Because just one thing, it won't tell you anything. But when you add them together, you have x minus x, s minus x, s minus x, s minus 1, s minus z, which we have here. And then what's left? 2x squared, 2y squared, and 2z squared. So now we found the answer. Just basically 250 plus 125 plus 200 minus 63 divided by 2, which we get to 256. Now, this is AP squared. This is not AP, right? We just multiplied, we just squared these. So actually, this is AP squared. So AP is going to be 16. And don't forget to scale it back in the end, which we get 192. Now in this question, we're thrown with the equation of two sides, and then their sum is 2. First of all, what will be the range of sine? Always remember, sine whatever theta is always going to be negative 1 to 1. If two sines, their sum is 2, then both sides has to be 1. No exception. Now we know this. Then we can know mx is this, nx is this. These are the general solution for sine x equals to 1. Like 2 pi over 2 plus 2k pi is the general solution. So we can write it like that. Now, we want to find a pair of integers m and n. So we might as well just divide them. We get this. After a little bit of counting, we get this. Because you factor the pi out, multiply by 2, we get 1 here, 4a here. Now, it's better to write it this way. Equals to k. We just want to find all m's and n's that satisfies this equation. Now, we do a little bit of casework. If k is 1, then m mod 4 is equal to n equals to 1. So this means we need to choose two subsets, two elements from this set. There's nine elements. Choose 2, which we get the answer. It's gonna be 28. Now, if k is less than 1, by multiplying m and n with the common constant, same constant, 1 over k, we have mc mod 4 is equal to nc equals to 1. Then either this exists or this exists. Because if you want to mod 4 equals to 1, you have to be an odd number. Now this we already counted, so we don't count here. And then now here, we count this. There's 7 numbers, you choose 2, which we get the total number is 21. Finally, if k is more than 1, note that k has to be an integer. That means mn belongs to the set or you do a little bit of bashing and you get this. So then each of m and n, you can pick them from there. So the answer is gonna be, you add the all previous one together, and you add C42, C42, C22, and another C22. You get the answer is 63. So now this question, we have an equation and we want 12 distinct real solutions. What first came to mind is try to graph the function on the left, but you found it's gonna be way too hard to do it. So now we're gonna make this function a little bit easier, and then we're gonna try to graph it. Now, what is important with absolute values is that they have a lot and a lot and a lot of choices. So we gotta do a bit of casework here. So we simplify the left side into this. Then we got C plus minus 21. This part's very easy. This part just like plus minus 21. And then you however C how much C you plus. Like here, here. As long as their difference is 42, it will work. Now the left side is a little bit more trickier, right? We're gonna do a bit more casework. Let's call this fx, the left side. So now fx is equal to negative 20x minus x squared. We factor out this first because it's easier. If x is less or equals to than 0, and 20x minus x squared if x is more than 0. Note that we put 0 here because it's easier. And then you solve the function. Try to figure out how much when it's negative and how much is positive. And you quickly realize it's 20, 0. The zeros are 20, 0. So you just write it out, basically. Now we have this. It's way more easier to graph now. So the graph will look something like this. This is a terrible graph, but it will look something like this. And you find the top part, the peak, is 10, 100, negative 10, 100. It's solved using these two functions, right? And then you know the maximum of them are 100. So now, we want 12 intersect points with two lines at the difference of 42. How would you do that? I already did it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's 12 intersects. So we're just gonna make sure the bottom one does not get lower than 0, while the top one doesn't get higher than 100. Then we always will have 12 intersects. Well, they can equal to 100 as well, and they can equal to 0. So C is gonna be this. So we got C is between 21 and 79. And then we get the answer by counting how many numbers are between 22 and 78. And then you get 57.